Hello, and welcome to a digital differential equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 2.2, Solving First-Order Linear Differential Equations. In Chapter 2.2, we look at a method to solve the general first-order linear differential equations in 3 steps called the integrating factor method. In addition to the integrating factor method, our author also presents the Euler-Lagrange two-step method. I will not use this method and will leave it to you to read further if interested. You are also not responsible for the Euler-Lagrange method on our exams. Let's get started with the integrating factor method for first-order linear differential equations. To solve first-order linear differential equations of the form y prime plus p of ty equals f of t, where f of t could be 0 in some cases. Remember, if f of t is 0, remember, say if f of t is 0, then our dE is homogeneous. If not, the dE is non-homogeneous. Now, we want to find what is referred to as an integrating factor called mu, or mu of t, such that when we multiply both sides of the dE by mu, we can write the left-hand side of the dE as an application of the product rule. So our general method is going to be find this integrating factor mu that we multiply on both sides of our differential equation. This then allows us to distribute the mu to each term, and it makes this left-hand side equal to an application of the product rule. Notice that in doing this, the function p gets sucked up by this product rule. Now, finding a function mu that does this will be tricky. I will have to justify this step to you. However, if we assume we can find this function mu that does this, we can then integrate both sides of the dE with respect to t and then solve for y. So we would integrate both sides with respect to the variable t. Of course, on the left-hand side, the integral of the derivative will cancel, just leaving mu y. And I can't really expand on the right-hand side further at this time because I don't know what mu and f, so it's hard to determine what the antiderivatives are going to be at this point. But they will be integratable. And then we'll solve for y by dividing both sides by mu. This will give y as a function of t. Now, I do not want you to remember this formula per se, but remember this series of steps that we use. Now, this method hinges on the fact that we're able to find a function mu that would do this. So to find a function mu that would do this, what we want to observe is that we need mu to make this equality happen. We need this mu y prime plus mu py to somehow be written as a product rule. This is what our method is dependent on, is that we can find a mu that does this. So let's take these two lines and let's look at what we can do with them. So we have the mu y prime equals mu y plus mu py. Now my method is going to be to manipulate just the left-hand side for a moment. So let's just manipulate this by applying the product rule. The derivative of mu y is going to be mu prime y plus y prime mu. Now that we've expanded the left-hand side, what I'm looking for is to cancel common terms. So notice this y prime mu here will cancel with this mu y prime here, since they're common terms. This leaves one term on each side of our equal sign. And out of those two terms, notice that we can cancel the y on each of these, which leads us to mu prime equals p mu. If we now apply the separation of variables technique to solve for mu, then we would obtain, and I didn't write the steps here, but I was running out of room, but we can write them on the side here. This would be d mu dt equals p mu. Separation of variables would say divide to get the mu on the left equals p dt. Here we'll integrate both sides. On the left, we'd have the natural log of the absolute value of mu. On the right-hand side, since I don't know what p is, it's hard to integrate this. So I'm just going to leave it as the integral of p dt. And now to solve for mu, I'm going to raise both sides with the base e. Using the property now that e and natural log are inverses, these two terms will cancel. And so I get the absolute value of mu equals e to the integral of p of t dt. And there'd be some constant from this, which I'd eventually rewrite as mu equals c e to the integral of p of t dt. Now in our problems, we're not going to keep this constant c in front. And I can argue when I do an example how that c will get absorbed. But this shows you how I find our integrating factor mu. Okay, let's look at how to apply this and maybe give a little bit more discussion. The integrating factor three-step method that I want to use to solve our first-order linear differential equations. So given a first-order linear DE of the form y prime plus p of ty equals f of t, we are going to find this integrating factor. Step one, we'll just find our integrating factor. Notice when we're looking for the integrating factor, we're always going to be integrating p of t, which is going to be just the coefficient of y. We will then multiply both sides of the dE by the integrating factor, then write the left side of the dE as an application of the product rule. We'll then integrate and solve for y. If we're given an IVP, we will then solve for the arbitrary constant for our initial condition last. Okay, let's look at an example. Find the general solution to y prime minus y equals t. Here we first look for the integrating factor. So our integrating factor is going to be mu equals e raised to the integral of p of t dt, where p is always going to be the coefficient of y. So here, remember our coefficient includes the negative sign. Here our coefficient of y, p of t, is just -1. So we're going to be raising this to the integral of -1 dt. Of course, the integral of -1 dt is just -t. Okay, step 2. Let us now multiply both sides of the dE by our integrating factor. So I have y prime minus y on the left times our integrating factor, e to the -t. On the right-hand side, we have t times our integrating factor, e to the -t. Distribute your integrating factor into your parentheses. Now, for most students, they actually don't show step 1 or this first line I've written. They'll just write the distributed form. So I write it as y prime e to the -t minus y e to the -t equals t e to the -t. Now remember, this integrating factor is supposed to have the property that it allows us to rewrite the left-hand side as an application of the product rule. Now, we can put a lot of thought into this each time, but what you could recognize as a shortcut, let me go back to our previous example, is that it's always going to be equal to the integrating factor times your original y. It's always your integrating factor times your original y. So here I'm trying to argue that I can write this as y e to the -t prime. Now, it only takes a moment to verify that this actually works. Remember, we have a product. We have the derivative of a product here. If you were to apply the product rule, you'd have the derivative of the first. The derivative of y is y prime times the second regular plus the derivative of e to the -t. Remember, the derivative of e to the -t is e to the -t times by the chain rule, the derivative of this exponent, which is this negative in front, times the first regular. Now, I'd like you to remember it's always going to be y integrating factor, but I think it's great for you to always verify that this does work. Verify that this actually does produce the correct terms. Okay. From this point, we're now ready to integrate each side of our differential equation with respect to t. Of course, on the left-hand side, when you integrate the derivative, those being inverse operations, just leaves y e to the -t. And while technically there's a constant, I'm not going to write it because there's also going to be a constant on the right-hand side that we'll use and combine together. Okay. I now have to look at how to integrate the right-hand side. And this is going to take on a variety of forms for us. Here, I would like you to recognize this as an integration by parts problem. So remember, with integration by parts, you have to pick a u function, a dv. We differentiate to find du. We integrate to find v. So here I'm going to choose to let u equal t, and the dv be e to the negative t dv. Remember, it's important. Oh, not dv. It should be dt. Remember, it's important here to have a differential on the right-hand side does equal a differential on the left side. Okay. We then find our derivative, which is dt, or 1 dt. Our antiderivative, negative e to the negative t. And remember, our integration by parts method says it's going to be u times v minus the integral of v du. So this allows us to rewrite the right-hand side as negative t e to the negative t minus the integral of v du, which is negative e to the negative t dt. Okay, let's simplify this a little bit. Let's pull a minus sign out and write this with this one as a plus integral e to the negative t dt. And let's look now at this antiderivative. Remember, the antiderivative e to the negative t is going to be minus e to the negative t. And then we'll have our arbitrary constant c. Now remember, we always wanted to solve this expression for y. So now let's divide everything by the e to the negative t. Notice that by dividing by e to the negative t, these terms will cancel, or those factors. These factors will cancel. These factors will cancel. And I think what we'll obtain is y of t is going to be negative t minus 1 plus, and so that I don't leave this as a fraction, I'm going to use properties of exponents to bring this e to the negative t to the numerator and write it as c e to the positive t. This is your general solution. Now, if you recall, this agrees with the last example we did in the chapter 2.1 guided lecture notes. This is the same solution that we found in our chapter 2.1 guided lecture notes. However, in chapter 2.1, we did it slightly differently. At that time, you might recall, you might want to look back in your notes to verify this, we were looking at the non-homogeneous principle. And at that time, they gave us this as yp, the particular solution to the non-homogeneous equation. And we found ce to the negative t as our homogeneous solution. And then we wrote the general solution as the sum of two solutions. I think us recognizing this general solution as really the sum of two different solutions is kind of an important technique for us, or kind of an important observation. Our homework will not ask you to look at your general solution and identify which part is the homogeneous part and which part is the particular part. But I'm going to be going through this in lecture because I think this is important to recognize. So make sure that you're looking for these as you do them in your homework. Okay, this completes your first example of us using the integrating factor method for solving first order linear non-homogeneous differential equations. I'd like to work a couple more examples with you just so you can see a couple more varieties of problems, but this should outline the technique I want you to be able to use. Let's look at another problem. In this problem, we're asked to find the solution to the initial value problem. So I've given you an initial condition. Now remember our set of steps. Step 1, we need to find the integrating factor. Our integrating factor mu is going to be e raised to the integral of p of t. So in our example this time, p of t is always going to be the coefficient of this y term. So here our coefficient is just 1. So we're looking at the e to the integral of 1 dt, which we know is going to be e to the t. Step 2, let's multiply everything by the integrating factor. So it's going to be y prime plus y times our integrating factor equals 2 times our integrating factor. Of course, we'll distribute the integrating factor into the parentheses and write this as y prime e to the t plus y e to the t equals 2e to the t. Remember, this integrating factor is supposed to have the property that allows us to rewrite the left-hand side as an application of the product rule. Remember, it's always going to be the original variable y times the integrating factor. And I want you to remember that, but I think also it's going to be important for you to just visual or just to verify this works. Take the derivative using the product rule. So remember the product rule, the derivative of the first is going to be y prime times the second regular plus the derivative of the second, and the derivative of e to the t is e to the t times the first regular. So we'll verify this always works. Okay. We then integrate both sides with respect to t. We use the property that the integral of a derivative are going to cancel, and so we just get y e to the t on the left. On the right-hand side, the antiderivative of 2e to the t is 2e to the t plus your arbitrary constant c. We now solve for y by dividing every term by e to the t to obtain y as a function of t is going to be 2 plus, and I don't want to leave this as a fraction right here, so I'm going to introduce a negative exponent to write this as c e to the negative t. Okay, Now, if we're given an initial value problem like we have in this example, we always want to find our constant of integration last. So now I solve the IVP. To solve the IVP, we're looking for the constant c that'll make sure that y of 0 is 4. So we evaluate our solution at 0, which is going to be 2 plus c e to the 0, and we know this has to equal 4. This tells us c has to equal 2. And so we have the solution to our initial value problem is going to be 2 plus 2e to the negative t. Now remember, graphically, we should be able to see this in our direction field. Remember from algebra class that 2e to the negative t is a decreasing exponential function. And this plus 2 is a vertical shift upwards of 2 units. So what we should see, starting at the point 0,4, right here, is a decreasing exponential function. Oh, I'm having a hard time drawing this, though. We should have a decreasing exponential function starting at 0,4. Should look something like that. Okay, now a little bit more terminology for you. We want to talk about transient and steady state solutions. Engineers are usually interested in solutions to differential equations that do not blow up over time, but rather settle into a constant or periodic solution. This desired long-term behavior is called the steady state solutions. On the direction field, we can sometimes see a whole family of solutions that are attracted to this steady state solution, while other parts of the solution, called transient solutions, will die out. Let's identify the transient solutions and the steady state solutions of our last example. So if we look back at our previous example, our transient solution, which I'm going to refer to as y sub t, is the part of the solution that decays or dies out over time. And here we want to know or see that that's this exponential portion here. As time goes on, e to the negative t goes to 0, which means that 2e to the negative t dies out as time goes on. While our steady state solution is the part of the solution that remains after the transient dies out, which I refer to this as y steady state, SS. So when the transient dies out, what's left is the 2. This is your steady state solution. This is the solution that things tend to approach as time goes on. So if I were to include in our graphic a couple other typical solutions, we can see that other solutions will, I can't draw very well today. other solutions do approach this steady state solution. Okay, let's look at another example. Let's find the general solution to this differential equation. Now, first notice this differential equation is not written in our standard form. To write it in our standard form, we always want to have the coefficient of y prime be 1. So if we solve this or if we make the coefficient be 1, we would divide each term by t, which will give us y prime plus 1 over ty equals 1 over t squared. We need to write it in this form so that we can identify p of t. So remember, p of t for your integrating factor is always this coefficient of y. This is the p of t we need. Now, I'm going to ask that you pause the video and work this solution out on your own. While the video is paused, I'm also going to work the solution out so that when you come back, you will see the solution already presented completely while I do it. So please pause the video and let's see what we can do. I'll see you in a moment. Okay, welcome back. I went ahead and written this solution out for this example. I hope that you've done the same thing. You might want to pause the video here for a moment to take your time and look through and verify that we do have the same answer. But in the end, I think that we should have found the same general solution. Of course, there's other ways you probably could have written this, but should be algebraically equivalent. But this is where I'm asking that you stop for this problem, is just to find your general solution. Okay. I have one more example for us to look at today. And the last one I want to look at is now an initial value problem. Again, I'm hoping when you look at this, you recognize that your given differential equation is not in your standard form. So let us first rewrite the differential equation. By dividing everything by the cosine of t. When we divide by cosine of t, I think we get y prime. Remember, sine divided by cosine is really tangent of t times y. And remember some of our trig identities, 1 over cosine is really secant of t. Okay. Now at this point, I'm encouraging you to again pause the video and work through this example on your own. However, I'm going to walk through it right now without pausing my video because I think there's some interesting integration that I want to talk about. However, I still encourage you to pause it, and if you get stuck, then come back and look at my solution. So here we go. Step 1, we want to find our integrating factor. So recall our integrating factor is always mu equals e raised to the integral of p of t. In this example, our p of t is the tangent of t. This is p of t. So we're going to be raising this to the integral of tangent of t dt. And tangent of t is one of those antiderivatives that a lot of students may not remember from calculus. At the time, when it was presented to you, it could have been presented as one of those antiderivatives you just want to memorize. However, you were shown how to find the antiderivative, and so I would like to remind you of that process today, but I'd like to do that as some side work. So let's go over here and do some side work. And I want to do side work just to figure out what is the integral of the tangent of t dt. One of the things that you probably remember from trigonometry, from calculus as well, is that if you're given an integral involving trig functions that you don't recognize, you may want to rewrite it in terms of sine and cosine. So remember, tangent of t is the same as sine of t over cosine of t. Now here, our method is to try a u substitution, where we let u equal the term in the bottom, the cosine of t. Of course, if u is cosine of t, du would be negative sine of t dt. Now, as you're following my work, make sure you're writing the notation correctly. You write your dt in all of these places. This is like, not writing the dt is not writing periods in like sentences. You need to keep correct notation. So make sure you write this dt. Now remember, when you do your u substitution, you're looking for your du to match something in your original integrand. Here I have sine of t dt, which we have, but without the negative. So if I were to solve for the sine of t by bringing the negative to the other side, we can say that negative du is really the sine of t dt, which matches a portion of our original integrand. Which now means we can rewrite this integrand as the integral of u in the bottom, since the cosine of t is really u. Sine of dtt is really negative du, which we remember the antiderivative of 1 over u. You can rewrite this if you'd like as negative integral 1 over u du would be negative natural log of the absolute value of u. Now remember, with these improper integrals, it's important to rewrite your integral or your answer in terms of the original variable. So this would be the negative natural log of the absolute value. Remember, u was really cosine of t. Now this answer is correct, but not how it's typically written. Remember, properties of logarithms allows coefficients to become exponents, which moves this negative 1 up to the top. And here I want to use the fact that whenever you have something raised to a negative exponent, you can rewrite it as a reciprocal. So this would be 1 over the cosine of t. However, remember, 1 over cosine is really the same thing as secant of t. And this is what I wanted you to recall as the antiderivative of tangent of t. Again, a lot of students just memorize this particular antiderivative like you remember the antiderivative of secant squared or cosine. However, if you ever forget it, this is something that you should be able to duplicate. Now, if we insert this back into our original problem that we were working on, then this now, we're looking for our integrating factor here. Then this now lets us write the integrating factor as e to the natural log of the absolute value of the secant of t. Again, using the fact that exponentials and logarithms are inverses, these would cancel, and we just get secant of t. Notice that I've dropped the absolute value. Now, I'm only dropping the absolute value here because I can make an algebraic argument that the absolute value is not necessary in our next step. Okay, let's continue. Now that we found our integrating factor, remember step 2 is multiply everything by the integrating factor. So now we have y prime plus tangent of t y times your integrating factor has to equal to your original right-hand side times your integrating factor. Let's simplify. So distribute the secant of t into the parentheses. Maybe simplify the right-hand side too. I think we get y prime secant of t plus tangent of t y times secant of t equals secant squared of t. Now here, the left-hand side of the DE looks complicated. But remember, this should be an application of your product rule. Sometimes recognizing this might be a little bit challenging, but what I like to do is recognize that I already know what this should look like. It should always be the original variable times your integrating factor. However, even though I write it knowing that it should be an application of the product rule, and I know it should be this, I still think you should check. So let's check this. The derivative of this product, the derivative of y is this y prime times the second regular plus the derivative of secant. Now remember, the derivative of secant is secant t tangent t, which is those two terms, times the first regular. So this does work. Okay. As we proceed, we will now choose to integrate both sides of the DE with respect to t. Now this is technically step 3, but I keep forgetting to write step 3 that I'm doing that. But this is technically step 3. Now we're integrating both sides with respect to t, which remember that means that the integral of this derivative are going to cancel. Oh, I'm writing an equal sign here. So it's going to be y secant of t equals the right-hand side. Remember the antiderivative of secant, the antiderivative of secant squared is tangent of t, and here's our arbitrary constant of integration, which technically would have been the sum of the two constants, or the difference of these two constants on each side. Okay, we now want to proceed to solve for y, so we divide everything by the secant of t. To obtain y as a function of t equals, now here we want to figure out what is tangent of t divided by secant of t. I want to simplify this. So let's do some side work over here. So remember, when we write tangent of t over secant of t, that this is the same thing as sine of t over cosine of t all over 1 over cosine of t. And you probably want to recognize that this is a complex fraction. It's a fraction divided by a fraction. So remember, when you're working with complex fractions, you will generally multiply by the reciprocal of the bottom. So this is going to be sine of t over cosine of t times cosine of t over 1. Of course, written like this, you'll see that these cosines will cancel. And so this ends up just being sine of t. So back to our original problem, this tangent divided by secant is really just sine of t plus 1 over secant. But remember, 1 over secant is really cosine of t. So this would be plus c times the cosine of t. And this is your general solution. Now we're not done though, because remember in this problem we were asked to find the solution to this initial value problem where we wanted y of 0 to equal 2. So now let's find the solution to this initial value problem. So we solve the IVP where y of 0 is 2. So let's evaluate our general solution at 0, which is going to equal sine of 0 plus c times the cosine of 0. And this should all equal 2. Remember, the sine of 0 is 0, and the cosine of 0 is 1. So this is going to tell me that c really equals 2, which gives us the solution to the IVP as sine of t plus 2 cosine of t. This is the solution to our IVP. Okay, this completes all of the examples I wanted to show you in Chapter 2.2 for solving differential equations using the integrating factor method. Now, if you'd like to see some more examples, I put several examples from different authors I found on YouTube on our Chapter 2.2 module in Canvas using where they solve other types of differential equations. So please look at those for more examples. Otherwise, I hope this will give you everything you need for your homework and will be a good point or a good place for us to start our discussion during our virtual class session. I'll see you next time.